There is a video that explains each and every tab that you need to specify a cooling tower to solve it. And in this video we're going to discuss the solve tab. So we've entered the atmosphere, entered the dimensions of the cooling tower, entered the operating conditions, we've specified the fill, and we've specified all the transfer areas that we want to include. We specified all the pressure losses that we're going to include in the analysis. If we want to specify the fan, here we've specified the fan that we're going to use, and it's going to use a fan because if we look under operating conditions, it tells us that we're going to calculate the fan, the airflow by using the fan curve. We've specified control parameters that help with the solution to know when to stop after convergence is achieved, and the output is not necessary, and the utilities, those are just extra tools that can help us to supply some inputs. And now we're going to focus on the solve tab. The software has three solution modes. It's the verification mode, a design mode, and a performance curves mode. So if you have a cooling tower, the design is in front of you and you want to verify if it will meet the design load, you can click on verify and you can enter in all the boxes the relevant inputs of the actual tower. If you select verify mode, nothing else on the screen is of any relevance. Only if it's design mode or performance curve mode that you need to enter in these boxes for the design and in these boxes for the performance curves and the relevant outputs given here. In verification mode, you only need to worry about clicking this button and ignore everything else on this tab. The other tabs, the info tab, residuals tab, and parameter values tab, gives you information and show you how convergence is being achieved. I've already run an analysis. I've already hit the solve button and it already completed a design. So if I click on info, it will show me all the parameters, the 5 design parameters, the time per iteration, and the total time. And here the total time to solution was about 22 seconds. Every iteration, it shows you the residual. So under our control, we've specified what the residuals for each of the 5 design parameter is. If we go to solve and we look at info, if the value is more than the tolerance, it is red, and as soon as convergence is attained for a specific parameter, it turns to green. The same happens for the air outlet temperature, and the last one that attained convergence is the pressure at 0.5. For a mechanical draft cooling tower, it doesn't calculate or doesn't need the pressure at 0.6, and here's the tolerance level for the mass flow rate of the air vapor mixture. Over on the right is a text box that will show you other pertinent information that for the iteration. It tells you that solution started. It gives you the initial values that you've selected. So if you go under control, it will calculate the initial conditions for you, and under solve it will just tell you what those conditions are. Sometimes for whatever reason, especially at extreme atmospheric and operating conditions, the values estimated here might not be realistic, so you can just pick it up there. If there are any errors, it just shows you the iteration number, and before it ends, it just tells you, based on an article from the literature, what the mass flow rates of the air and water are, and also the ratio between them. and what is acceptable according to this one source, and then the solution ends. The next tab, residuals, is just giving all these residual values in graphical form, and it's updating after every iteration. Here's the tolerance levels that you've entered under control for every design parameter: the water outlet temperature, the air outlet temperature, the air vapor mass flow rate, and the pressure at 0.5 and the pressure at 0.6, which in this case it's not calculated. And this is the residual. So if all residuals are below the selected tolerance levels for that specific design parameter, then convergence is achieved. And just to make sure that convergence is achieved, we go to the parameter values. So this tab is showing the residuals, and this tab is showing the parameter value. So you can see the initial value of the water outlet temperature. If we go to info, we can see that the water outlet temperature was estimated to be 36.5 degrees Celsius. If you go to parameter value, it starts there or thereabouts. So after the first iteration, it is 35, and you can see that it's converging to its final value. Also for the air temperature, air outlet temperature, there's a big spike up and then it converges. The relative smoothness of these convergence profiles is a function of, under the control tab, the relaxation parameters. If we've selected relaxation parameters that are a lot larger, the convergence wouldn't have been as smooth, as I will show you shortly. To show you the importance of selecting small enough relaxation parameters, I went to the control tab and I've increased the relaxation parameters for the 5 design parameters to 0.4. I went to solve and I hit the solve button, and I stopped the execution after 20 iterations. I went to control and hit stop. At the end of that iteration, the execution stopped and it indicated it as such here. So you can see that because the relaxation parameters were not small enough, the solution actually is diverging. It's not converging to a final solution. So yeah, just look out for that. If your solution is not converging, go to the control tab and select small enough relaxation parameters. Typically, relaxation parameters between 0.1 and 0.3 generally leads to convergence. Now we're going to do a live solution of a cooling tower. So we've entered all the data. We go to solve. And before we solve, I highly recommend that you click on info and then run check inputs. So if you click on that, it will look at all the inputs and see if there are any apparent input errors. So here for the dimensional inputs, there's a warning. If it's a warning, the program can still execute, but just take note of that. So here it says that the fan cover ratio may be too small. It is less than 35. In this case, it is 34.9, so it should be fine. So if we are happy with that, we can hit the solve button. When you hit the solve button, it will do the input check again. And then it will continue on to the solution. And here you can see the speed of convergence. If I go to the residuals, you can see after every iteration, the residual graphs update, as well as the parameter values. So if we go to info, you can see that the air outlet temperature already met the tolerance level. We can verify that in this graph. You can see that's already under the tolerance level, and now we are waiting just for the PA5, and now that happened. It's yellow, this status button, if the solution is still going on. If it's finished and successful, it will turn green. We can do a final check by going to the Info tab, and it says success, convergence achieved, and solution ended. Now we can view the outputs. So now we go to the Output tab, we click on that, and now all the different outputs are given in this table. It's the main outputs, the full name, some inputs that you've selected, then the cooling range, the water outlet temperature, the approach, the duty, that is 20 kilowatts, the evaporation rate, so 7.789 kilograms per second water evaporated, and that amounts to 1.9% of the water that evaporated. Then there's the different flow rates, the air inlet and outlet conditions, then the water outlet conditions, the density of the outlet water, then all the pressure drops in pascals over all the different sections that we've specified. It gives the loss coefficients, the transfer coefficients, and then some mechanical draft parameters, the volume flow rate. So if you want to specify a fan, the volume flow rate is 3.95 and the total pressure drop is given here. And by using those two, you can specify a fan. But because we've already specified the fan in the solution, we can go to the fan performance, and we can see that it found a solution on the fan curve. Now the fan curve that you see here is not exactly the same as the fan curve that you selected here, because it's a model fan for this one. But by applying fan laws, if you go to the output, this is the actual fan curve at the operating conditions and the size of the fan. So this dashed line over here, that is the system resistance line, and where that line intersects with the fan's static pressure curve, that's the operating point. And here's the fan shaft power. The output is given in kilowatts, although the inputs was in watt, and we haven't specified the curve for the fan efficiency, hence there's no fan efficiency over here. If we go back to the summary, we can export this table to Excel by clicking on that button. Let's click on it. It will open this window, and we can specify the location of the file, and we can save it there. Then if we click on pressure drop, it will tell you the percentage contribution of the pressure drop throughout the tower. And in this case, because of the specific fill that we've employed, the fill is not the largest, which it usually is. But in this case, it's a very splash type fill with not a lot of resistance. So the drift eliminator is more, fan upstream losses are more, and the inlet louver that we've specified is also fairly high resistance. Then if we go to the transfer areas, see that about 70% of the transfer contribution is from the fill, about just over 20 from the rain zone, and just less than 10% in the spray zone. If we click on the psychrometric chart, so we've specified the first dot in the beginning under atmospheric conditions, but here it's calculated to be on the saturation line, and that is the assumption that the Merkel method makes, is that the air that exits the cooling tower is saturated with water vapor. So that is the outlet state of the air. Then we can go to the cooling range. That's the water inlet temperature, water outlet temperature, the cooling range, and the maximum possible outlet temperature for the water, or the minimum outlet temperature for the water, is the wet bulb temperature. And the difference between those two values, that's the approach, that's 5.33 in this case. And we can look at the full performance. So this is just a visual representation of the empirical equations that you can find under the transfer areas, under full specification. This equation with these coefficients for the transfer coefficients, and on the pressure loss side, if we go to the fill loss coefficient, it's this equation with these coefficients. The output is just showing those curves visually with water loading rates from 1 to 5 and the operating point in between, and you can see the same for the loss coefficient on this side. If we go back to the psychrometric chart, we can see that, and we've already mentioned that the outlet air is saturated with water vapor, and that is because we've used the Merkel method. If we are very interested in what the outlet conditions of the air are, then we have to use a different model. Then we can use, if we go to transfer areas, we can select the Popper model. If we do that, we have to adjust these equations that we've used because they were generated by using the Merkel method. So if we select 1.07 as the Merkel number for the Popper method that you calculate, that's generally 7% higher than what you get with the Merkel method. So if we rerun it, then we hit solve and then hit the solve button. Then we can wait for convergence to take place. It's first doing the input check again, and then it starts with the solution. This time around it might take a bit longer because the Popper method is a much more rigorous approach. It doesn't make the simplifying assumptions of Merkel, and it will calculate the air as it moves through the cooling tower. With the Merkel method, only the inlet point was known, and then we've estimated the exit point that it's saturated with water vapor, and we didn't know any properties in between. But with the Popper method, it calculates it along the way, and in this case we've only selected, if we go to transfer areas, we only selected 5 levels. So if we go to solve, and let's just wait for convergence to take place there. Also, a nice approach that one can do to speed up convergence, if we've done the analysis with Merkel, we can go to control and then click on the use current solution as initial solution. So there shouldn't be big differences between the outputs that we get from the Merkel and Popper approaches, especially with these parameters. So if you then run it with the Popper method, the initial solution is already close enough to the final solution that it will take a lot longer, a lot quicker. And this is especially important for cross-flow cooling towers because it's a two-dimensional problem and it takes a lot longer than counterflow cooling towers to solve. If we go to solve, we can see that it's approaching the tolerance level, and the only one that's still not under the tolerance level is the outlet water temperature. But we can see from this graph that it's already close to converging to a final solution. Let's go to info, and it's a 1 or 2 iterations away from converging. There we go. So everything converged. The status lamp will change from yellow to green, meaning that we have a successful solution. If we go to the output, now you can see in the psychrometric chart we've selected 5 intervals, so 1, 2, 3, 4, 5, and you can see that now we've calculated on those 5 levels the state of the air as the air moves through the cooling tower and through the fill, and you can see that the outlet air is actually not saturated with water vapor, but the humidity is 90%. So in this case no plume will form, as the outlet air will move back to the atmospheric conditions in a straight line, and because the line never crosses the saturation curve, there will never be plume problems for this cooling tower at these atmospheric conditions.